Okay, let us get started. This month, the question we are answering from a customer, they ask, I am confused. I saw a presentation at the 2019 DataStax World Conference detailing how to deliver a product recommendation engine. So customers who bought X bought Y. A product recommendation engine using DSE Graph. Additionally, I suppose, I've also seen DSE articles detailing how to deliver the same functionality, a product recommendation engine, using DSE Analytics. So, which is it? That is the question we're going to discuss here. All of this content, the program code, the data, a PowerPoint, well, this PowerPoint deck, this video you found, a white paper, all of this is available on GitHub, and to make the spelling easier, it's available at tinyurl.com. tinyurl.com/DDN3000. DDN is short for DataStax Developers Notebook. If you're looking at this video far into the future, you'll want to center in on the July 2019 content. If you are a CXO, presumably a CTO, you're most interested probably in 5 or so slides at the end of this presentation. Prior to that point, we look to make our case, to show you the code, to do the compare and contrast, say when one is better versus the other. We do a little contrast with SQL also. So actually, after we prove our point, there's about 5 slides at the end you care about. You can skip ahead. From your perspective, this presentation details 2 categories of analytics that many customers don't have. They may have one, they don't have both, and many people do. So you might be slightly behind the curve. If you're from the business side, we would say for at least a number of years there have been analytics capabilities available that will help your ability to upsell, cross-sell, better maintain or better provide service for high-value customers, etc. This presentation is centered on product recommendation, but you will clearly see throughout how this can be applied to other areas of your business. And if you're technical, I'm technical, it has been mentioned already, we'll give you all of the code, we'll demo, or we'll show you all of the code. You can take the code with you. We'll show you how to make these things happen. It's all fully documented. It's all available for your download, including the data, etc. So our agenda. We're going to show in detail how to deliver a product recommendation engine, customers who bought X, bought Y, using DSE Analytics. Also, how to deliver the same functionality using DSE Graph. And the point is to compare and contrast. Each delivers a product recommendation engine, however, in a slightly different, in slightly different ways, certainly, but to a slightly different purpose, and that'll make sense when we get in the slides. And as a result of this compare-contrast, we expect, we had intended to also answer why and when would you use a graph database. When I first encountered graph databases, that was my question. Why would I need to add new things? Why do I need to learn new things? Why is this better? I would imagine that's a question you have also. As we are detailing how to do this with analytics and with graph, in the graph area, this series of documents has offered primers and introductory on a lot of topics. We've never done a graph query language primer, and this document, this presentation would serve to do that, so that's cool. We'll get that out of the way. And while we've done other articles on analytics, this one's a little tighter. It's a little more to the point, a little more concise. So, graph databases. It seems to me, perhaps if you're anything like me, I'm sorry. But also, the first question would be why. I'm perfectly happy with SQL. I'm perfectly happy with whatever NoSQL I already have. Why do I also need graph? That is a question we believe we answer in this presentation. We'll cover in analytics. We'll cover graph. Along the way, we cover why. I know we cover why. And hopefully, we will get that question answered for you. It was frustrating for me when I first encountered this topic and answered this question. And as my boss would say, you get one of those bullshit hand wavy responses, pardon my French. So we're going to hope to knock that down. And enough with the hand wavy, we're actually going to detail that. For someone to say that a graph database is a more natural way to think or model data seems a little in contrast with relational databases. Relational databases have been around for 40 or so years. They are the de facto standard still for most people. Wouldn't that seem to be a more natural choice? In the area of graph databases, at least, we're going to say that the topic of what you are doing would be organized into at least modeling and then also the query language. And here we're considering just modeling. So in a relational database, we would have the classic one customer begets one or more orders, an order begets one or more order line items. You bought 5 things on the same Amazon.com order. A relational database, while they support one-to-one relationships, and we'll talk about that another time, or they may have many-to-many relationships, and what does that mean in a relational database? Primarily, 95 or more % of the time, they are focused on one-to-many relationships. And it is a decomposition of whatever it is you're doing business with. So customer, one-to-many orders, one-to-many line items. Everything is stored once, non-repetitive, third normal form. And in many cases, when you want to use that data, you have to reassemble it. A joke we used to make at a document database company that I worked at, which was denormalized. It was a document model. It would be like parking your car in the garage, and every time you do so, you have to disassemble the car into its 14,000 requisite parts, right? Why would I do that? And of course, if I want to leave the garage and drive somewhere, I have to join and reassemble all of that data. Excellent idea back 20, 30, 40 years ago. When disk was expensive, was probably one of the business drivers there. Not automatically the best idea today. In a graph database, we do model differently, but still similar enough that it's not going to throw you for a loop. So here we have customer ordered stock. We tend to focus in graph databases on the relationships between two entities. And in this case, we have customer, we have stock on shelf, and the way that customer relates to stock on shelf, if they in fact relate, is they have placed an order. In a graph database, the primary data entities are called vertices, and they're basically SQL tables. And the relationship between two vertices is called an edge, also represented by a table. The vertices tend to be nouns, the edges tend to be verbs. And unless you've only placed one order, or I suppose you don't have a relationship, you place no orders, the relationship is almost exclusively one-to-many, and then out of the edge, it's a many-to-one. So we're focused primarily on relationships between the primary entities, which we call vertices. And that's all interesting, but still, why do I care, right? I'm still getting hand-wavy. It doesn't seem that much different from relational in the area of modeling. At least it didn't throw me for a loop. And tables are tables, relationships one-to-many. There's just not that much difference here. But that is our charter in this presentation to show why graph would be different from relational, why graph is even different from machine learning, predictive analytics. And how we hope to do that is we're going to give you the detail. We're going to show you how to write the code. Is it more code? Is it less? Would it be easier to maintain? Is it more performant? And as a result, then we hope to get away from the hand-wavy stuff and actually give you the why do I need a graph database? When would I use a graph database? And customers who bought X bought Y. Excuse me. A product recommendation engine is just the vehicle. So if you've read any of the editions of the document that you're in now, in this series, you've seen this image before. However, it might be new to some of you. The product we're using to deliver this product recommendation engine, the software product we're using to deliver this stock recommendation engine, is DataStax Enterprise. There are 4 primary functional areas of DataStax Enterprise, and they are listed here. One of the 4 is the commercial offering of the open source Apache Cassandra product. It's DSE Core. DSE Core is always on. It must always be on. It is not optional. It's the storage tier, and without it, we would not be able to persist data. A second functional area of DSE is DSE Search, known in open source as Apache Solr or Lucene. So spatial indexing, text analytics, basically all of our indexing other than primary keys at this point. By the way, I need to mention all of the information you're receiving in this video and in these materials are relative to version 6.8 of DataStax Enterprise, which is currently EAP controlled release, subject to change, legal disclaimer. Search can be turned on or turned off. It's optional. It's basically an indexing engine. It gives us additional query processing, so you can look for data in a polygon, which you couldn't do with Core. DSE Analytics is the commercial offering integrated within DataStax Enterprise that would be known as Apache Spark in open source. Spark comes with a number of things. The core abstraction, the central object within Spark, is the data frame or the RDD, beautiful implementation of a parallel processing engine, data engine. And then additionally, they have streaming, same object. They have ways to join and document your Spark jobs. And they also have machine learning, which is why we're going to use DSE Analytics here. 28 or more routines, supervised, unsupervised, various routines. The one we're going to use is product recommendation. And then graph, which is we're going to do product recommendation also using graph. So 4 primary functional areas of DSE, there they are. We're primarily going to speak about 2, analytics and graph, but we also accidentally use the other 2 while we're here. So DSE Analytics, again known as the open source Apache Spark. There's many areas within Spark, and we are focused on machine learning. Love, love, love this definition of machine learning. Definition as listed: machine learning, an algorithm whose accuracy improves given more data, which is spot on. The more order data we have, the better that this product recommendation engine will be. All of the machine learning routines, more data, greater accuracy, hands down. If you know nothing about machine learning, within Spark, there's 28, 30, 35, perhaps, depending on how you count. There's flavors of the same routine. Supervised, unsupervised. Unsupervised would be essentially the columns are not labeled. So if I do a clustering, if I'm looking at customer churn, what are the properties of a customer that identify that they might be getting ready to discontinue my service? I might throw whatever numeric measures I have of a customer, if it was telco, if it was cell phone, how many domestic minutes, how many international minutes, how many lines in the plan, how many months have they been a customer, all numeric, unsupervised. And the routine will essentially keep graphing on an XY coordinate plane, a Cartesian plane, the various points and see how what the distances are between similar or to be discovered dissimilar customers, churn, not churn, unsupervised. In supervised, we know what's in the columns, and in addition to them being numerics, they could also be text. We're going to be working with grocery data, so like milk, bread, eggs, cheese. That was your first clue. This was going to be supervised. And also just frequent pattern matching, which is, or mining, what this is called, is categorized under supervised. Again, about 28 out of the box, years and years of maturity, highly parallel and performant. 5-6 years ago, the documentation was not great, and you were pretty much reading source code. The documentation, at least for the last 2 years, is outstanding. And you could largely teach yourself machine learning just by reading the Spark machine learning documentation. Spark has chosen to be available on JVMs, on Scala, Java, also Python and R. So you're not writing your Spark machine learning coding in C#. You're just not doing that. As soon as I say that, I'm sure somebody out there has built something in the open source, but as far as, or as some sort of side project. But as far as Apache goes, it's these 4 languages. Hugely vibrant ecosystem. Anything you Google will resolve. Top 3 answers show exactly how to do it. It is open source. It is fabulous. At the bottom, we have some URLs. The first one is the page listed. And the two categories here, how do I do this? It's been a while. The two categories here, one of these is old. RDD based is an older representation of these same machine learning libraries. And today you would use the libraries under MLlib. So focus largely on the ones on the top. And then we drilled into frequent pattern mining. There's two options there. We used FP growth is the more common and certainly suitable for our needs, and it's the one we're going to document here. There are other machine learning routines, certainly churn, as we might have mentioned earlier, etc. But we're focusing on frequency pattern mining. Depending on your software adoption maturity curve, where are you? Are you bleeding edge version 0 type person, or are you more conservative, which is perfectly fine? You might not yet be certain if there is an application for machine learning or if it is real. And these are a little fun. Two quotations from back in the day, Herbert Simon, 1965. Machines will be capable by 1985 of doing any work a man can do, and that has not come to be. And then Marvin Minsky, another famous gentleman, he won the Turing Award. Within 3 to 8 years, we will have a machine that will have the general intelligence of an average human being. And why did that not come to be? It didn't come to be for a couple of reasons. They're brilliant men, certainly, but since they made those proclamations, we now have access to just reams of data. We didn't have this data before, and that's burdensome if I don't actually have purchase data in order to do purchase recommendations, and I don't have it nationally across 8,000 stores and various demographics, right? The availability of pizza boxes, fast, parallel, cheap computers. I can just throw tons of hardware at this. And also back in the 60s, they were focused on AGI, general intelligence. And we got a little smarter and said, well, let's just try to solve small problems first, like customers who buy X bought Y. Hundreds of people working on this every day. Universities through grants, general researchers, obviously companies like Amazon and such. I meant to and did not complete doing a Google for an Amazon statistic. We've seen older statistics floating around, how much they think page loads and slower page loads will impact their revenue. But who's on record as saying that our product recommendation engine generates X dollars per day per month? I failed and didn't look any of that up for you because honestly, to me, that would be considered common. The fact that that is a real thing is common knowledge. And not to be underestimated, but open source and social coding, what people are putting on GitHub and other, is making a significant contribution in advancing machine learning. Good job, them. So while there are 28, 30, 35, depending on how you count, machine learning routines just within Apache Spark, aka DSE Analytics, and you need to choose a routine, generally the flow is thus. Once you have a routine, it expects data in a given format. In machine learning, frequent pattern mining, they expect a single column. And as we're looking at a grocery order, we'll say you bought 10 things, you bought 20 things. They want them to be comma delimited. Single column, comma delimited. Different routine might want it differently. We mentioned churn as unsupervised. We'll take numeric only columns. They don't even have to be identified. The churn routine will normalize them another day, another time, and do its plotting and calculations just based on numerics, as many as you want. 10 columns, 40, 110, whatever you want. So they expect a given data format. It will build a model, which is abstracted across all of the routines. The model is obviously a data structure, but how it is formatted is different per routine. Each model in each routine, calculating the model could be CPU intensive or not. There tends to be a relationship, however, if the model is CPU intensive, memory intensive, whatever, calculating the model is resource intensive, then applying the model tends to be really simple. But if the model is really quick to calculate, then applying or scoring the model. Let me give you an example. Classification. One of the seminal use cases for classification is you have a bird feeder in front of your house. A bird lands, you've never seen the bird before. What type of bird is it? So you have a database of all birds. And some of the things in your database of all birds are the foot type. Is it webbed? Does it have talons? The beak, is it sharp and hooked? Is this a predator? Is it a spoonbill? So it's a possibly a waterborne bottom feeder. Width of the wingspan, weight of the bird, color of the bird, etc. So you don't know any of this until the bird lands. And now that you have this data, you have to now, for the first time, go against the body of data and try to figure out, is this a hawk? Is this a duck? Is this a whatever? So calculating or scoring the model, taking the bird that's landed, now going against the model and saying, what type of bird is this? It's the scoring that's intensive. Just recording the data up front is not a big deal, but scoring it later and saying what type of bird is this is the intensive part. You'll get a given response. Whereas, say, with our example that we're doing, product recommendation engine, it's the building of the model, which is intensive, and we'll show you the algorithm and you'll get a sense of why that's intensive. Scoring the model, figuring out what the response would be, you have a flashlight in your shopping cart, you need batteries. It's a primary key lookup, it's a super fast scoring. So beat that to death, but either building the model is intensive or scoring the model is intensive, and it tends to be an inverse relationship. You need to know that because scoring the model, if you're trying to apply this in real time, what is the application of that? And then product recommendation engine, of course. I'm an old angry man. I probably don't buy the same things as a pre-teen, little boy, little girl. So applying demographics, right? I buy different things than someone who's not of my age and degree of angriness. But we'll start with product recommendation, and we'll probably cover demographics another day, another time. And also the topic of refreshes. So we get more data over time, or can I do A/B testing? Hey, this is a great model. It seems to be getting me some really good results, but hey, let's try this. It's a different season. It's Amazon Prime Day. People are crazy. Are there other recommendations I should be making? And we'll be talking about that. You've heard this before, the graphic on the right. Machine learning is a discipline in and of itself. However, 80% of machine learning data scientist time is spent just preparing the data, getting access to the data, correcting the data. Is it in different units of measurement, metric versus imperial? Different calendars. Is it on a 12-month calendar? Is it on a 13-month, 4-week period calendar? ML, as it is now well documented and as it works ridiculously fast within DataStax Enterprise and other, is actually the easy part. In this same series of documents, I can't remember when, I want to say April of 2017, but don't quote me on that, I wrote the first part of this machine learning product recommendation engine 2 years ago, just as recently as 2 years ago. And a product recommendation engine in Apache Spark was delivered using something called an a priori algorithm. That has since been replaced. Why are we still talking about it? We'll talk about the a priori algorithm because it's easy to understand. You'll see the thing that upgrades performance-wise the a priori algorithm, and it gets quite a bit into vectors and such. It's math heavy, where a priori algorithm, I mean, a little bit of Python knowledge. You could write it in Python. It wouldn't be very performant, but you could still write it and it'd be accurate. So what is the a priori algorithm? So on the left, we have grocery data. We have 5 orders. The first order has soy milk and also lettuce. The second order has lettuce, diapers, wine. Chard is, what is that? It's a type of onion, I believe. I think I'd know. So I have 5 orders. Each order has a number of items. Going through the first step of the a priori algorithm, we go through the list of orders and we first generate a list of unique single items. You will see why. A unique list of single items. So just lettuce, just wine, just soy milk, just OJ. And this tends to be called candidate item of size 1, aka C1. And after we have the list of unique items, then it's a nested loop. It's 2 for loops. Within those items, then we get the pairs, C2. And after we get each pair, we get lists of 3 possible items, 4 possible items, etc. So C1, C2, C3, C4. What are all the unique items you could buy? What are the unique item pairs you could buy? What are the unique item triplets you could buy? And as we're calculating these singles, pairs, and triplets, as we're looping, we calculate 2 values, support and confidence. And we still do this in the new improved performance algorithm, support and confidence. How we loop is different and better and more performant. But support and confidence are still, they're still part of it. And support is defined as the item set count, and we'll explain that in a moment, divided by the total order count. So the total order count in this case would be 5. I have 5 items in my database. I hopefully would have millions, right? But the total order count is 5. And as I'm calculating the support for just soy milk, what number of these 5 have soy milk? And in this case, it's 4 out of 5. And that's why we're using this tiny little data set, because it's easy to see, it's easy to calculate. So the support for soy milk is 80%. Okay, big deal, I don't care. The reason we define support and calculate support is it's necessary for confidence. It's also going to be necessary for something called lift, which we'll show you in a second, but certainly confidence is a make or break. And what is the definition of confidence then? So if we look at the combination of diapers and wine in this list as opposed to just diapers. So the combination, a C2, candidate item set of size 2, an order with 2 items containing diapers and wine has happened in 3 of the 5 cases. Diapers, wine, diapers, wine, diapers, wine. It's the middle 3 cases. But diapers has happened in 4 of the 5 cases. Thus, the confidence I have in diapers, wine is 75%. It's 3 divided by 5 divided by 4 divided by 5. And this is all based on math, more math than just division. And what we're looking for is we're looking to drop low confidence items. We don't want to stick them in the database. We don't want to continue to calculate their support and confidence. Why? Because they never happen. If I have 1 million items and something has only happened twice, why am I calculating this? Why? If in the entire history of Home Depot, I've only sold 2 chainsaws, why am I going to recommend selling you a chainsaw if you come in and buy whatever it is you buy at Home Depot? So on a low confidence, these events happen with such infrequency that I'm not going to continue to carry the weight of them in my database or in calculation, which explains the term a priori. In Latin, a priori means from before. And so the 2 mathematicians, one guy was from University of Madison, I'm drawing a blank where the other guy was from. Shame on me. So they used the word a priori because it means as I encounter low confidence item, I discard them from my list. And why that's a good thing is if a C2, if an item pair has a really low confidence, if never has it happened that somebody bought a chainsaw and a baby stroller, it just doesn't happen in my store, well then not only is that pair infrequent, but the third item that could possibly be purchased with that pair is even less frequent. And so I don't need to calculate the C3 from a C2, which is low confidence. You get it? And that's what they mean by from before. We start discarding low confidence items to optimize the time spent building the model and then also storing the model within the database. From this data, we only have 5 rows, right? So let's not get too excited. But if this diapers wine pattern maintains itself over millions and millions of rows, it happens 75% of the time. That's off the chart. Apparently, we have the diapers and wine store. Then if somebody picks up just diapers, should I suggest wine or wine? There's actually a difference, by the way, between having wine and adding diapers and having diapers and adding wine. And it has to do with the frequency of the C1. If everybody buys wine, then my confidence that diapers add wine, right, versus wine add diapers is different, and that's because it's in the denominator, and it'll tank your confidence. So all of the terms, and if you master the terms on this slide, you can master frequent pattern mining. There are no more terms than these currently to memorize, and you could give a talk and you could be expert at frequent pattern mining. So we define support on the previous page. It's the item divided by the order counts. And then confidence, and we start discarding rows with confidence. We discard it in the 2-year-old algorithm. We discard it in the current algorithm because they just don't happen that frequently. But then here's the next term, and this is where hopefully you're really sold on the legitimacy of this math. So we define lift, and this is as hard as it gets. And I apologize, I forgot. I need to define antecedent and consequent. So simply think of what ante means. It means pre, and con means post. So antecedent is the numerator, and consequent is the denominator, or in this formula, or the pre and the post. And hopefully this will make sense, the antecedent and the consequent, but we're going to use these terms here when defining lift. So lift is defined as the support of A union B. And if we're looking at an order of lettuce and soy milk, and then we're considering wine, should I recommend wine to these people? They bought lettuce, they bought soy milk. The whole point of this is a recommendation engine. They bought lettuce, they bought soy milk. Should I recommend wine? And the math for that is the union of A and B, which in this case would be lettuce, soy milk, wine. If you look at this sample data set, that's happened 1 out of 5 times, that's 20%, divided by the support of just A, lettuce, soy, times the support of B, just wine. So lettuce and soy has happened in 4 orders, wine has happened, I'm sorry, not 4, let me count it, lettuce and soy. 1, 2, it's happened in 2 of 5 orders, or 40%, and wine has happened in 3 out of 5 orders, or 60%. Do the math, 40% times 60%, get that, it's within parentheses, order precedent, and use that to divide 0.2, and you get a number equal to 0.83, or 83%. 0.83 is a better way to say that. If lift is 1, and I honestly don't have these memorized, so I'm going to read them a little bit. I know that I need a value greater than 1, and 2 is better than 1, as 3 is better than, the greater the value larger than 1, the effectiveness of this rule should be higher. So if the lift is equal to 1, there is really no association rule that I can or should derive from these two events. If and let's go to less than 1. If the lift is less than 1, one item has a negative effect on the other and vice versa. And to the point that one item could, in cases, be considered a replacement item. There's just no reason for me to draw a strong association rule out of this. Association rule is what we're going to use to recommend you bought flashlights, you should buy batteries. Even though it says that one item could be substituted for another, we don't use a low lift to generate replacement items in and of itself. We would do further machine learning, but certainly it's a candidate. And then what we are looking for is a lift higher than 1, and much higher than 1, the better. So 3 is better than 2, 5 is better than 3 and 2. And it implies the probability that the antecedent and the consequent are dependent on one another and could form a useful prediction rule. We're going to have some data here in a moment. While we were using 5 rows of data because they're easy to count and do the math, and I super apologize, I got a list of grocery data somewhere on the internet in the last 10 years, and it was before I was really bothering to keep, like, where did I get this from? So I cannot attribute this to someone. I apologize. I don't know where this came from. But here, using a larger data set, and I forget how many rows are in this data set, probably more than 10, I don't know, but it's in the distribution that I'll give you. It's a sizable number. And here you can see that a lift of 3 or higher is not unreasonable. So from this data, we'll just look at the top line. If you bought yogurt and whole milk, I should recommend to you buying curd. Or if you buy fruit and other vegetables, you need some potatoes. You need some root vegetables. Is carrot a root vegetable? Whereas if the lift was calculated to be 1 or less than 1, I probably shouldn't bother to make this recommendation. You might think I'm crazy when I do this on the website or I do this somewhere else. Antecedent, consequent. So antecedent is what they bought. Consequent is what I'm going to recommend. What is the lift? Higher the number, the better. And then just to show you a little bit, you might start thinking, well, how am I going to put this into production? We often, within our own model, and this version doesn't even, like version 2 doesn't have to be later than version 1. They're just labels. So you could do A/B testing. Like, hey, 48 states in the continental U.S., something's going on in Oregon, and I want to treat them differently and do some testing. Maybe some special statewide event, who knows, right? But so I could version this. I could put this into my query when I get an antecedent. Say, give me version B, give me version A, give me version C. And just build that into the select statement when you then try to calculate and see what the consequence should be. By the way, we're talking about the calculation of the model being resource intensive and then inversely the scoring of the model being the inverse. So this would just be a primary key lookup based on yogurt whole milk. So this is going to be 0 to 4 milliseconds, 0 to 8 milliseconds. This is going to be ridiculously fast. Getting them the response, a scored response of, hey, have you considered buying curds and putting those in your grocery cart also? So the model is resource intensive to calculate, but scoring the model, finding the proper consequent is quite simple actually. So the a priori algorithm, we talked about get all the unique items, get all the item pairs, item triplets. You can start discarding some if they have a low confidence. You could code that, right? That's really easy. It's just two nested for loops. But as you might have imagined, those 2 for loops are rather resource intensive, right? You could be looping for quite a bit of time. In the April 2017 article, I believe, I actually showed you the math. If you had 100 unique items, it is a ridiculously high number of possible pairs and triplets. I mean, it's a factorial. It's not a deal breaker. You'll still calculate the model within a second or 2 seconds. It's not awful. It's a parallel enabled algorithm. Throw a couple CPUs at it. Even on a laptop, it's not hard. But still, it was slower than it needed to be, more resource intensive than it needed to be. So about 2 years ago, Apache Spark went from basically arrays to a frequent item set lattice. So basically, and I hate that I'm going to do this because we're going to talk about graph later. It's basically it's a network graph of data. It's a lattice, and it's just a little. Well, it's quite a bit more resource efficient than doing it via the a priori algorithm. And we had mentioned earlier that machine learning was the focus of many companies, universities through grants, etc. This is where you're seeing that. I'm not terribly bright, but I could have told you that the 2 nested for loops were brute force, and certainly there had to be a faster, better way to do this, and lo and behold. So the newer version of software doesn't use the a priori algorithm, it uses a frequent item set lattice. It's a lot faster. It's at least 10x and approaching 20x faster. And if you're running a bunch of machine learning, you would care. And then all of this is integrated within DataStax Enterprise. So if you had just upgraded your DataStax Enterprise, you would have got this faster algorithm. It would have been 17 times faster. Fully integrated within DSE. So all of this can use the indexes from Solar, Lucene, blah, blah, blah. So same logging, same security, same HA. I talked about this a little bit earlier. So after you had built the model, somebody's on your website and they're like, okay, I want to buy some lettuce. And you want to come back and say, well, you got lettuce, you really should get something else. And I threw this select statement up before I thought about, well, okay, obviously we're going to apply this. So we had sorted by consequent and then confidence, but really what we should have sorted by was first lift, the highest lift. And I'm not heartbroken that we're going to talk about you could have run different selects for the scoring, because what if OJ is out of stock? And you're really trying to push chard. You have a bunch of chard that's going to expire, right? So there's lift as a pure numeric sense would have been the best recommendation, but there's other factors we could have run to best manage our inventory and get an upsell, service the customer by reminding them of things that they want, but also keeping our prices low by selling stock that we want to get rid of, that we have too much of, or they may be getting ready to go out of season or getting ready to spoil. That's what it's doing under the covers, and I want to show you the code. So this is where the CXO can check out and move forward and more. So all of the code, I think I've got about 5 steps. Remember that Apache Spark could be written in Scala, Java, Python, or R. If I'm just doing some throwaway, I'll probably put it in Python. Scala, by some people's estimation, would be a better choice. Python machine learning is probably more popular. So line 1, you have to import the library. So we're importing Spark ML, frequency pattern matching, and if you recall from the doc slide we had, there was actually 2 algorithms we could have chosen. FP growth works for me just fine all day and all night. So we import the library we want to make use of. This is all the code. So I put everything in here. You could actually run this code. It would run. This is one line here. It's a data file. It's a CSV. And it's a grocery list. This is the 5-line grocery list. There's a 10,000 line plus grocery list called grocery LG, large. So in Scala, what this does is read a CSV and pull it in as an object called rex0. As it turns out, there was no schema to this CSV to talk Spark, to talk Scala. There was no schema. One data line could have had 2 items. Another one could have had 7. You could have bought 100 things in an order. So that's not a normalized schema, right? It's just a CSV, a comma separated value list. And so this next line, what we do is we say, okay, but it is basically a single data set. It's the items. I want you to split it on the comma. And now I'm going to call this is a Scala thing. Instead of calling it rec0, I'm going to call it rec0s. These next 2 lines, and this first line here is split. It's actually 1 line. These next 2 lines make the model. That's how hard that is. So given a CSV, and I got to munge it a little bit and split the comma separated values, rec0 would show up as an array per line, First, this val my FP growth just gives me the object that I can calculate a model into. And we set the support and the confidence. What do those do? That's the conversation we had earlier where we said if something doesn't happen frequently, forget about it. Get rid of it. I don't want to calculate it anymore. Don't want to stick it in my database. Doesn't happen anyway. Why am I calculating this? Why am I incurring the overhead? So you set the min support, set min confidence. If you set it to 0, you'll calculate every possibility, and a bunch of them never happen. So 0.1 is 10%. And that just gives you the object forthwith the model will be created. And you know who actually makes the model? It's the fit verb method. And even though there's 28 or so plus routines, 30, 35 routines, consistently all of the Apache machine learning will use the verb fit for calculating the model. So that's nice. There's a consistency there. So when you see fit, fitting a model or calculating a model. So at the end of this, you could start recommending product with 2 lines of code to make the model and then maybe 2 preparatory lines of code to get ready to make the model. That's how hard that is. E.g., not hard. And at the end of that fit, you could say association rules show. You don't need to do that. This is a nervous tick I would have. I want to see what's in the model. Apparently, this model has 4 columns. Antecedent, you know what that is, consequent, confidence, and lift. And we're probably most concerned about lift greater than 1. The higher the number, the better. And these association rules are what you would use to score. So in the case of soy milk diapers, matter of fact, both these lines, these are recommendations I might want to make. Soy milk diapers, soy milk OJ. If I don't know anything about you, I guess diapers and OJ are a tie, right? 1.25. That's where I might get into my further customization of what do I have on stock. Or if I was really sneaky, I know where you are in the store because you're on my Wi-Fi and you're closer to OJ. I'll probably, or if I'm, they know if you have babies, believe it or not. So you probably don't need diapers if you're me. Dog diapers maybe, but not human baby diapers. That was gross. My dog doesn't need diapers. We'll erase that later. But I'm probably not going to recommend lettuce if you bought OJ diapers and soy milk and whatever else is in that line 1, because there just isn't enough lift there for me to think that I'm going to win that one and avoid just being excessively noisy. So if I already have a model, what's all this junk? The model is in memory. And Spark, Apache Spark, who's giving us these libraries, is storage agnostic. Officially, it's storage agnostic. As we deploy Apache Spark as DSE Analytics, knows all about DSE Core, knows all about Cassandra, knows about how to co-locate data. That's great. That's something that we added. But it doesn't know how to write to a database. So I need these lines in order to write to a database. First, I'm going to use a library. I need to import another library called wrapped array. Why? Because Scala gave me, I can go up a page. Scala gave me arrays for the antecedent and the consequent. That's what the square brackets mean. Machine learning library gave me arrays for the antecedent and the consequent. And the way I want to store it in the database is I don't want it as an array. I just want it as a string. It'd be a whole lot faster to look it up just as a string. If I was really fancy, I'd store it as a numeric int, but that's another story for another time. While we had done an association rules show that didn't capture it into a variable. And so I want to capture it into a variable. I'll use the collect method. So now I have a handle on the model. And I'll take this model and I'll apply a transform to it. I'll take those two arrays for antecedent and consequent and I'll build strings. That's what this does. Make string, make string. I need to get the confidence and lift as doubles and I return it as an array. This is all one line, by the way. It's just a long line. Scala is a fluent API, meaning you can say do this, dot, do this, dot, do this. You can just append to the command. It's how they program. And so map is a transform, taking the first column, which was an array, make it a string. Second column was an array, make it a string. Third and fourth columns, make certain they're doubles, and return that to me as a list is what I needed to do here. Now, this variable rex0 association rules as list, ARL. I just pulled that out of thin air. Didn't have a schema, so I want to call the columns antecedent, consequent, lift, confident, and list. Why it didn't have a schema is because map kind of stepped on my schema. And so I do a show to show now that association rules as a data frame, ARDF, has a schema. Here it is. And what that means is I'm really ready to write it to a database. DataStax Enterprise, the storage tier is the open source Apache Cassandra. We, DataStax, make Apache Cassandra. We're the commercial entity behind that. That's good. That means we pay for it to be advanced, supported, bug fixed, secured. And we're not terribly stupid, so SQL is prevalent. So our primary command language for Cassandra is called CQL, Cassandra Query Language. Looks pretty much just like SQL everywhere it can. So we're going to create a table called T for table association rules. It's got 4 columns, plus I'm going to insert another column called version. That's where we're going to add number 1, number 2, or A and B. I guess I called it a double, so it's going to have to be a double. And I partition keyed on antecedent, so that'll be my lookup key. And I can sort by consequent and version. A little bit of Cassandra internals there. So then writing to DSE Core, I had yet to add the literal 1.0, or if it wasn't a a decimal. If it was a string, I would have made it an A and a B, something to say, look, I'm going to have multiple versions of these rules over time, and I want to treat them differently. I want to do a recommendation in Oregon different than a recommendation I do in New York City different. So I'm gonna version those. And then actually the write to the database is here. It's a save with append. I could have done an overwrite, but that would kind of ruin my whole versioning thing. So how many lines of code was that total? 2 to make the model, and the rest was handling CSVs versus strings versus arrays, and then adding this version, labeling the schema so the column names map up, make the table, and writing to the table. That's how hard that was. So hopefully you could, with this guide, certainly make that happen in your own time. If you have a DSE engine running, and we'll talk about this later, I use Apache Zeppelin, an open source web-based client, to just do little scripty Scala, 10-line Scala. With those 2 pieces of software, you could implement all of that. And you'd have a product recommendation engine, and you know how to do the scoring. So a little bit of overview then. And I'm somewhat repetitive at times, I apologize. So it was 2 lines of code to make the model. All the other lines of code were to prepare the data set to look like what the model needed on input, and then take what the model gave us and make it equal to what we wanted to store in the database. I could have stored the antecedent and consequent as arrays. Very possible within Cassandra, within DSE Core. I didn't want to do that. I know it'll be faster as a string, and I'm all about speed. I want to make that recommendation just that fast. And then your takeaway, because we want to do a compare and contrast between this and Graph. This is a content-based recommendation engine, aka product. So given a list of orders, I see the frequency with which people buy flashlights and batteries. You just have flashlight in your cart. Don't forget the batteries, right? This is kind of funny. I was on one of the building websites. I won't say who it is. And I needed to buy a washer dryer. I had it delivered. I live in the middle of nowhere. They drop it on a dirt road on a curb. There's no curb. And so I picked my washer, and I'm like, surely they're going to show me the dryer I need to pair with this, right? So they look the same. They're the same color. Stupid thing kept showing me more washers. I already had a washer in my shopping cart. I don't need a second washer today. Thank you very much. And at least they labeled it customers also viewed as opposed to customers also purchased. So, but this was content, flashlight and batteries. Apparently there's some correlation between diapers and wine. But the point is you have the products. You have the history of orders of product, item, product. Graph can do this too. And while the library that comes with DSE Analytics, aka Apache Spark, was written for us, it's parallel, it's well documented, it's got all the metrics. If for some reason that algorithm wasn't working for you, you could rewrite it, certainly in Scala, write your own routine, or you could write it as a graph query. So Graph could do a product too, but where Graph really differentiates over DSE Analytics is collaborative based, user. And that's a different application, and we'll talk about it, and hopefully then you'll get content-based versus collaborative-based, just item data versus maybe I don't have the item data. It's a brand new product. Nobody's bought it yet, but I still want to see if I should recommend it to you. Then I would look at user. And we'll show that in detail. So I kind of said, when would you do collaborative based? You don't have the product data, but you still need to predict something, perhaps something that's new to market or something that has never happened. Moving from product recommendation using DSE Analytics now into DSE Graph. So I don't presume that you've seen DSE Graph, so I apologize. We're going to show you every command in detail, what it means. Hopefully you find that useful. If not, you can skip over a couple slides. But now we're going to go to the second half, which is product recommendation using DSE Graph. The example we're going to use, before we're doing grocery, this time we're going to do movies. And we're going to say it's a brand new movie. So it's not like I'm recommending Charlton Heston Omega Man for you, right? Which came out in, the 70s. This is a brand new movie. It's not even going to drop till Friday. How could I possibly have any date on that? But maybe you're a reviewer or you have a friend who's with a paper or something like that. One guy saw the film, loved it, and there's a relationship between you and he. You have N friends in common. You not only have people you know in common, but you tend to rate the same things highly or the same things as a low, you have similar interests. And since you have some connection to this person, relation, and you have similar preferences, I can still make the recommendation even though I have no history on the product. And that's a collaborative product recommendation versus an item. The product isn't available for sale yet. That should have been your first clue. And we made a distinction earlier saying, when do I need a graph database? And we said, the modeling is different, but it's not that different, but it's different, but it's, so we're doing all this, oh, it's great, right? Hand wavy. The model is slightly different. It certainly has some different names. Tables are called vertices or edges, and how we store the data is different. But really the differentiation between graph and SQL certainly is the query language. Hands down, 90-10. And we're going to see that over the next couple of pages, and hopefully you get it. So if you don't delete the video right now and fail to complete any portion of it on this slide, then I'm impressed. So this is actually the full query necessary to do a collaborative product recommendation engine. Now, I'm not terribly stupid. I can imagine you're not expert at graph databases. Most people are not. Most people have never seen them. You know SQL, but you do not likely know the query language for the leading open source graph database, which is called Tinkerpop. The whole thing's called Tinkerpop. And the query language in specific is called Gremlin, hence the little gremlin on this page. There's no way you know Gremlin. 100 people could be watching this video, IT people at random sample. 2 know Gremlin, 3 know Gremlin. Most people just are not aware of the value of a graph database. So I don't think you can read this is the point. On a 10 scale, 10 being high, this query is about a 4. It's not that hard, but you've never seen it before, so of course you can't read it. You don't know graph. So we're going to pick this thing apart, and we're going to show you how it works. I will say this, though. Hopefully you're not just looking at these slides on paper, otherwise you wouldn't hear my voice. But some of these might even stand out. Like you could imagine a dedupe step removes duplicates for some reason. You could imagine an order by, what an order by does, and we're ordering by the average rating per user, hence mean decreasing. I want the high numbers first. I want to rate the things that are, or return the things that are highly rated first. I only want to see 5. So even if you know SQL and don't know graph, you know what an order by is, you know what a limit is. The last line value map, that's just formatting how I return my column list. You could guess what a dedupe is. You might guess what a filter is, but I'm not going to hold you responsible for that. You could probably guess what has a rating greater than or equal to something is. So I'm going to say a couple of these lines will make sense to you. The brown lines are hard. If you've never seen graph, you have no idea what those are. And so we're going to cover all of these. We're going to pick all of these steps. That's what these dedupe, where, and order by are called. They're called steps. SQL would call them clauses. We call them steps. One of the differences. So we're going to explain all of these on the slides that follow, and I hope you being of at least average intelligence, and if I do a good job, you'll come to understand everything we're doing. Just a little bit compare and contrast because we're trying to answer why and when graph. So let's visit our old friend SQL, and specifically the SQL Select, which is the cornerstone of relational databases and SQL. So a SQL Select, select column list from table list. Those are 2 clauses. Select column list from table list. Those are 2 mandatory clauses that must be in every SQL Select. Without select column list from table list, you don't have a SQL Select. You must have those 2 of 7 clauses in a SQL Select, or again, you don't have a SQL Select. So these are mandatory, and they must appear first. After that, there are 5, depending on your SQL implementation, up to 5, maybe 6, maybe 4. Optional clauses that can appear in a SQL Select. Where is very common. It applies a query predicate. It restricts the result set so you don't have to read the entire database. It also specifies join relationships between 2 or more tables. The clauses are where, group by, having, order by. Most people have a select and a temp table. But the point is, of these 5 optional clauses within a SQL Select, these 5 optional clauses, if present, can appear one time only and must appear in order. You cannot have 2 group by clauses. And you might argue that if I need 2 group by clauses, my data model is wrong. Yeah, okay, I'll go with that. But it would be handy to have 2 group by clauses or yada yada. And how SQL tends to overcome that is they have a bolt-on top of selects called common table expressions. Each of these SQL selects tends to be a single pass top-down. It creates a result set, 0 or more rows. And then the CTEs can do basically intersections or diffs or what have you, unions, which is redundant to a SQL select, of those resultant data sets and try to get you more power behind the SQL select, because as a 7-clause total query language, SQL it's limited. It's showing it's, given that there's other options out there now. Beautiful in the day, and in a multi-table select or in a single table select, some of the things that SQL is trying to determine for you is the access method per table. Am I doing a sequential scan or an index scan? I have multiple index technologies. Do I use a B tree? Do I use a hash? Do I use an R tree? And when you have 2 or more tables, should I read table 1 first, then drill into table 2, or table 2 first, then drill into table 1? And based on the properties of this query, should I join rows between 2 or more tables using this algorithm or another algorithm? Most of the serious modern commercial databases will have that. The order of execution in a multi-table select statement, SQL select, tends to be filter, join, sort, FJS. Let's say you have this select, a 2-table select. After it's figured out it's going to read table 1, drill into table 2, it applies a filter on table 1, or if it was reading table 2 first, then join, then sort. How it determines table order is it generally looks for the most restrictive, most efficient application of the query predicate of a filter. As efficiently as possible, reduce the number of rows that need to be processed. And so in this where clause, we have the 2 tables are joined. That's pretty much a thing. If call 4 equals x, if say call 4 equals x was really like gender code, male, female, and it's going to return half the contents of T1, that's pretty useless. And I should be smart enough as a database to apply this predicate, call 5 equals y. Hopefully that's much more restrictive, much more efficient processing path to do it that way. And that's the responsibility of the database server to figure that out for you. But as you're going to see in a moment when we get into graph, this is still a very high-level abstraction. The whole point of SQL and SQL Select is a declarative programming language, which means you say what you want, but not how to get it. They might have optimizer hints that says, please use this index, please do this table first, but you really cannot control, you can't program how it's really processing the rows within T1 or T2. To go farther to explain and justify that, we'd have to talk about maybe OR-topped queries. Anyway, you really cannot control what we're going to call traversers, the actual processing within a pass to get any of the data. And we'll be able to show that better when we get into graph. It's basically relational algebra, unions of sets, intersections of sets, add, subtract. Yeah, they have CTEs. They have common table expressions as a bolt-on top of selects. I find them complicated to read. I still find them limiting. Very often they force temp tables as opposed to just in-memory streaming data. But it is what it is. SQL is what SQL is. Graph databases, while they call their tables something else, vertices and edges, but they're basically tables, it's the query language, hands down, that differentiates graph databases. And it's a much more capable query language, so comparable to SQL, it's harder to learn. It does more. Where SQL is a declarative, SQL Select is a declarative programming language. You just say what you want, not how to do it. Gremlin traversals. Gremlin is the equivalent of the SQL language in graph. A Gremlin traversal, a Gremlin query is imperative programming. So it's like saying for loop, nested for loop, on every iteration do this. You're actually programming, have the ability to program the query. If you hate that, stop watching now. If you're intrigued what that may offer, keep watching. It's an imperative programming language, and it's also functional programming, if you know what functional programming is. If not, I'll stop there. And not only that, Not only is it an imperative programming language, at the same time, it is an associative programming language. One of the 40 some odd steps within Graph, I guess I'm going to be hand wavy because I don't actually talk about that in this presentation. In your whole 100 table database, you can say, I have a customer in Denver, and I'm shipping them something from Minneapolis, and you're the database. You tell me Houston's going to flood. Houston has no relationship to Denver, the customer, or Minneapolis, the warehouse. Hurricane's going to hit Houston. Is this customer going to be impacted? Is this order going to make it on time? And I can do that in SQL, but if I have 100 tables, I got to write 100 tables select. And because those relationships may not be present, they're outer selects, which are a little bit more costly. And that query is going to be 95 pages long, right? Try maintaining that. It's going to be several pages long. Try maintaining that. Graph, the point is, has a step called match. And it says, you're the database, you figured out. Can I get from Minneapolis, or does this routing, or does this order of Minneapolis to Denver, does it have an association with Houston? You tell me. You're the database. You have all this data. You do the work. So it also does associative queries, and that's actually one of the more seminal use cases of a graph database. Today we're doing product recommendations, so we're going to use the imperative nature of queries within Graph. But another day, another time, I should show you the power of associative queries. It wasn't the question you asked today. So there's 40 steps, plus or minus, depends on how you count. And the steps can have step modulators. They impact how the step is configured or then accessed later. And but the cool thing is it's a fluent API, so I can use the same step 2 or more times and in any order. So it's basically a query framework specifically for a graph database. You can now, rather than just declaring what the query should return, you can say how the query should execute. And if that scares you a little bit, there's certain queries where you need to be able to do that. DataStax Enterprise still supports SQL. If it's a SQL query all day and all night, write it as SQL. We do joins using DSE Analytics. We do primary key lookups of single tables, redundant data, classic NoSQL. We do it all. We still do SQL, but there's some queries that you're going to want to do graph. Here's your first graph example. I haven't turned on the pen yet. Let me turn on the pen. So this is a full-blown query in graph. G is a reference to the connection handle. You could have called it something other than G. Everybody calls it G. It points to a single graph. Think database within the entire server. And V says, I'm going to start on a vertex. You actually could have started on an edge. You could have started by querying the relationship between two entities, not the entity proper. Has username Dave. What this means in English is there's a vertex called user. It's a table name called user. So look only in that list. Your query could have specified no vertex names. It would have looked at every vertex in the system. You could have specified 3, some subset of vertex names. Here we're saying 1 vertex name. And we're saying there's a column in graph, we call them property keys, with the value of Dave. So start with just Dave in the user table. And then leaving the user table out, going out from the user table, go out via who does Dave know. So the first time I do this, I find out who Dave knows and repeat this 2 times. So after I get the people who Dave knows, I go out and get the people that they know. So with a level of separation, who is Dave's circle of friends? And after I have who does Dave know and who do they know, who is everyone within Dave's circle of friends as defined by this distance of 2, emit and return that to the calling function. Now, certainly SQL can do recursive joins. Certainly it can, right? We know that. So big deal. Why do I need graph yet, right? The point here is this is a baby query. This is a hello world. And as we get into the product recommendation engine, you're going to see that this is just much more functional. I threw this up here because I wanted to show you a query. Recursive joins are not overly common. They're not required. But graph, as it is the nature of it being based on relations, it's funny, relational databases, SQL, are called relational databases when it's just always a drill down. It's not really who knows who. SQL didn't even have recursion for the longest time. parts of material, explosions, circle of friends. So anyway, I chose a recursive query, and it's who does Dave know and who do they know, and then return it to the calling function. And this is a Fluent API. So g.v. G.v with no arguments would return every row and every table in the database. Don't do that in production. Has is the next method. Repeat is the next method. Do it twice is the next method, and then emit. But this is all one command. It's like one SQL select. Using the Fluent API, it's all one command. So this dot this dot this. I could have had another has below. I could have repeated something else below. It's Fluent. The order is optional, and yada. So the model we will primarily use in this product recommendation engine for movies. Every database platform on the planet ships with a sample database. The one that ships with DataStax Enterprise is called Killer Video. It's basically like a Netflix or a Hulu or Amazon Prime. And users rate movies is where we're going to spend the most amount of time. Users rate movies, but as we look at Circle of Friends, users know users. So there's a recursion there. We don't need to really worry so much in these examples about who were the actors in the movie. We don't care per how we've written this. If you like Clint Eastwood, right, we could build that in there. And then, are you just looking for a horror movie today? What genre does it belong to? Don't freak out if you see something called knows to or user to. I do that a lot of times for my testing. I'll make little side copies and call it version 2 or something like that. And I didn't clean it up for the graphics. I apologize. And not only are we going to use Killer Video, but at times we may just make some edges and vertices off to the side because it'll be simpler. A recursive join of who knows who might throw you for a loop if you're not practiced at doing that. So I'm also going to use customer orders at times because it's a little simpler. It's something you're more common or more used to. A couple of steps. I think there's 4 steps or 4 progressions in the creation and understanding of product recommendation using Graph. We're going to start with who do you know. By volume, this is about 5% of the query, and we're going to spend about 1/3 of the time on it just because you've never seen Graph before. So all of the code, end to end, who do you know? And do you actually know them? So we're going to make 3 tables. So we're doing this outside of Killer Video. Why are we doing it outside of Killer Video? Because we're going to add like 10 rows of data so you can absolutely see Farrell knows Denise, Farrell knows Q. If I throw you into a 10,000 user database, that's another reason I create side copies. A lot of times I'll prototype on 5 rows of data just to prove to myself it's doing what I think it is doing. It's a good practice when you're getting started. So we'll make a table called user. The user has an ID, a gender, and an age. We copy those attributes from Killer Video. And then who do you know? And know is an edge. And it says it, in this case, it's a recursive, so it goes from user to user. So we store Bob knows Charlie, Albert knows Denise. So very commonly, the edge is just the join pairs. It would be the customer number and the order ID for customer orders. Edges can actually have their own properties, but I didn't need that for just this example. So users know other users. I wrote, this is production capable code. So users know other users. When you go out on an edge, when you say, who does Farrell know? You're going out on that edge with a direction. We used to automatically make those edges bidirectionally. And so we would store the data. We would store 2 copies of the data. We'd store who do you know and who knows you automatically. Well, if you're not actually using the reverse direction traversal, that's kind of a waste. And so in version 6.8, edges are no longer automatically bidirectional. Edges are made bidirectional by creating a materialized view on the edge table and just flipping the columns over. So let me draw with the mouse as soon as I take a drink of water. So it's hard because this is a recursive join, and I apologize, but that's where we are. Users know users. So here's the edge. Who do you know? And S is short for source, and D is short for destination. So if I was recording that Farrell knew Jim Hatcher, I would put Farrell as the source and destination as Jim Hatcher. And the primary key is headed by source. Who does Farrell know? If I want to go the other direction, who knows Farrell, I'll go from Farrell source to destination. Good to go? So automatically edges in the prior release of the product were automatically bidirectional. We found that you weren't using them as a customer well over 90% of the time. Why are we incurring that overhead? One of our value propositions to you is that we are always ridiculously fast. Why are we doing this if we're not using it? And so it's fully documented, blah, blah. In order to make a edge bidirectional, you create a materialized view. What is a materialized view in Cassandra? Automatically, when I insert, update, and delete data in nose, it's automatically pushed to the materialized view. It's automatically maintained. Consistency is maintained. And the effect here is I have a different anchor to the primary key. I can serve a bidirectional traversal of an edge. Did I beat that to death? I wanted you to know about that. And we actually do need a bidirectional traversal of who do you know in this example. Here's the data we're going to use. So we have some users. The users are Farrell, Denise, Hatcher, Morty. We have a couple users. My boss's name, Q. Coolest guy on the planet. Great boss. He'll never watch this video. He'll never hear that, but he's still a great boss. And then those are the vertices. Those are the people. Those are the nouns. And the edge, knows is a verb. Who knows who? Farrell knows Q. Farrell knows Denise. Farrell knows Mortimer. Farrell knows Jim. Farrell knows 4 people, and 2 people know, 3 people know Farrell. Notice that while Farrell knows Q and Q knows Farrell, because there is a difference. I know who Bono is from U2, right? I know who he is, but he has no idea who I am until he watches this video. So I need to record that. So Farrell knows 4 people. 2 people know Farrell. Notice that Dave knows Farrell, but Farrell has no idea who Dave is. And this is going to be something that we do in the example coming. So make some tables, make some data. So here's your first query towards the collaborative, the user-user product recommendation engine. So we define a variable called LUser, so this is reusable, and we're saying we're going to look at this from Farrell's perspective. We're going to start in the entire graph, g.v. We're going to start at all vertices, but I'm just going to look at the vertice called user. And within the vertice called user, I'm going to look at the user ID where LUser equals Farrell. So I'm just going to look at Farrell in the user table. And I'm going to say leaving user on the edge, who does Farrell know? Leave and figure out who he knows. Who does Farrell know? Start with users, leave on knows, who does he know? And return all columns and the user ID. In addition to the 8 columns you have in a table, vertice or edge, the 52 columns you have in a vertice or edge, in addition to those, you have additional control columns called ID and label. And why is that handy? When you're first learning and you start doing traversals, you go vertex to edge to vertex to edge, you may not, as you're learning, you may not know what vertex or edge you landed on, so you can return the ID and the label. The label is the name of the vertex or edge that you're getting data from. And it's useful for debugging. I don't know that you would use it for anything else. So this query says start at the user table, filter on the user ID equal to, in this case, Farrell, and show me who he knows. And value map, give me these control columns, and blah, blah. So the data that is returned are the 4 rows of people who Farrell knows. I know Denise, I know Hatcher, I know Q, I know Morty, and if we go up a page, that should probably be true. I know Q, I know Denise, I know Morty, I know Hatcher. I don't know Dave. Who else is in here? Pretty much, I don't know myself, but that's implied, right? I don't know Dave. So these are the 4 people I know. So if when I go out on user and say, who does he know? Boom. This would be like select star from table in SQL. So I've learned the has step, I've learned the out step, and I've learned the value map step. Out. Of the 40 or so steps in Gremlin, could be 38, could be 45, could be 50, could be higher based on your version and how you count. There are a subset of steps called traversal steps. They're basically the commands, the steps, that allow you to traverse from vertex to edge to vertex to edge. You never go vertex to vertex. You never go edge to edge. You always go vertex to edge. You could go back to the same vertex, but it's always vertex, edge, vertex, edge, vertex, edge, vertex, edge. You can branch from any of those. You could split the stream, and we'll get into that a little bit later, but it's always vertex, edge, vertex, edge. Of these traversal steps, some are only appropriate when you're sitting on a vertex. So you can go out from a vertex, you can go into a vertex, you can go both in and out to a vertex, but the verb, the step, out is not appropriate for an edge. If you're sitting on an edge, you can't go out from an edge. I'll explain that in a moment. Focusing on just vertex. When I leave the vertex, if I say out, I will go through the edge, but I will land on the outgoing, adjacent vertex. I use the edge to specify the relationship. Farrell knows whom, but with the out, I will land on the out, the remote vertex. So if this was user likes movies, I'd wind up on vertex 2. I'd wind up on movies. It's a little weird that we have a recursive join user to user, but that's where the problem starts. I need to know who you know. And if I was sitting on vertex 1, we'll have an example where I will say, well, who knows me? How I answer the question, who knows me, is I would come in from the users through knows. And if I want both, who do I know and who knows me, I would use both. The point is that in, out, and both will land you back on a vertex. They start at a vertex and they land you back on a vertex. And they are vertex traversal steps. If you don't want to go from vertex to vertex, you want to stop on the edge. Why do you want to stop on an edge? That seems stupid. They're just join pairs. They just specify the relationships between two vertices. The reason you might want to stop on an edge is the edge can itself have properties. We'll see that example later. When user rates movie, one of the properties of the edge is the rating. I'll have a unique list of users. I'll have a unique list of movies. When you rate a movie, did you rate it a 10? Did you rate it a 0? And if I want to evaluate and do work on the rating, which is a property key to the edge titled rating, then I would want to use out E or some form of. I left the vertex going to the edge. It would be out E, in E, or both E. Now, once you've landed on an edge and you want to go somewhere, there are edge traversal steps. And where do you go from an edge? You go to vertices. So that's why they have V's in them. So if it's not apparent to you, the reason these are vertex steps is you can't go from edge to edge. You can go from vertex to vertex or vertex to edge. From an edge, you can only go to the adjacent vertex. Adjacent means that they have a direct relationship, right? Users rate movies. They are adjacent, and when you're talking specifically about which movies did a user rate, it's the incident adjacent edge. It's actually a movie you rated. So there's 40 or more steps in Gremlin. These are the vertex and edge traversal steps, or just traversal steps. How do I traverse from entity to entity, from vertex to edge, or most commonly probably vertex to vertex? So this would, and even the first query we did are kind of like the hello world of graph. So we knew that Farrell knew 4 people. We ran that in the previous query. But who does Farrell know? Who knows Farrell? And I guess, who knows Farrell and Farrell knows them would be also in that list also. So just, if we just did an out from user knows to user, I would get these 4 rows. If I did just an in, I would get Dave, because Dave knows Farrell, but Farrell doesn't know Dave. And as a result of both, I get also a common list of data. Denise knows Dan, Q knows Dan, Farrell, and Farrell knows them also. So both will give me data. And here's another application looking at the ID and the label, which we get from true. You can see actually embedded in here what the keys are, which is sometimes handy for debugging. Both as a traversal step is actually a vertex traversal step. So the the label is actually a vertex. Both is a vertex. So it's going to go from one vertex to a vertex. Thus, the data that is returned is actually a vertex. I label my vertexes V something. You don't have to do that. And I label my edges E something. You don't have to do that. I find it handy. But you went from vertex user back into vertex user because it's a recursive join. And you had not only who does Farrell know, who knows Farrell, and who knows Farrell, but Farrell doesn't know them. So I got 7 rows of data here through the both. And then this query coming in to this edge, or coming into this vertex through the edge knows, these are the people who know Farrell. Doesn't mean I know them. I'm Farrell. So these are the people who know Farrell, which could be different than who does Farrell know, because I don't know Dave. I know Denise and Q, but I didn't have to. So in are the people who know Farrell, but not automatically, right? So that's interesting. I can run a query of who does Farrell know and who knows Farrell. But if I want to guarantee that we know each other, that's a thing, right? I know Bono. Bono doesn't know me. But if I want to know that these two users know each other, I'm going to use an additional step. And this step is used for this purpose, and it's used for other purposes. And the step is titled as. So it's one of your first new steps. And why do you need as? As you ran this query, as you started from user, knows user was the previous example. Just so happened you went back to the same vertex, but as you said, vertex, verbs, vertex, you wound up on a distinct vertex. Unlike SQL, and for efficiency sense, when I'm sitting on vertex V2, could have been customer places order. I'm sitting on order. As I'm sitting on vertex V2, customer places order, I'm sitting on order. The only property keys that are in scope by default are those that would be located on vertex V2. I do not automatically go customer places order and carry all these. Can I do that? I do not automatically carry all of these columns through the edge, take all the property keys from the edge, carry those to the next vertex. Dude, there are queries where we could go through 42 vertices. It's a very complex query. Or just, it can get complex. And the amount of data could balloon and go ridiculously crazy. So unless you explicitly say, I want to keep the attributes from V1 and E1 when I arrive in V2, unless you explicitly say to carry those attributes with you as you traverse, you don't have them. And how you have them is use the as word, or the as step. So there is no default trail for a traversal, which is a good thing because it wouldn't scale. It would be awful from a performance standpoint. But if you do need those attributes, you can easily and without penalty, as long as you need them and you're going to use them, carry them with you through the traversal using as. There's 2 other steps that might seem similar to as. They are store and they are with sac. Compare and contrast. As will allow you to carry columns forward through the traversal. It's just like taking columns from customer and carrying them forward to order because I want to run a query that shows me customer properties and order properties, just like SQL. So you will use as. Think of it as a carry forward of property keys. For some reason, store is just like as. You can carry columns forward, but they are derived columns. So they're like aggregate expressions or literals or anything that you just picked out of thin air or used other columns to derive values of. There's a reason it's not just called as, it's called store. And I'm going to wave my hands in the air a little bit. We're actually going to use with sac and sac. There's also aggregate group and subgraph. Every one of these has a distinct use case. The as and the store, the things that you carry forward or derive, are global to the query. They're global to the traversal. In this context, traversal is a synonym for query. But it is very possible, and there are use cases where you don't want a derived value, certainly, to be global to the entire query. And where you'll see that is when you do group bys. Like say you have 50 states or provinces in the United States and you're doing calculation per state, you won't use as and you won't use store. You'll use with SAC and SAC. They are local to a traversal, and in this context, it would be a subgrouping of data. It's a very programmable query API. Aggregate, I'm pretty certain we didn't need and didn't use. We didn't use group. Subgraph, we didn't need. We just needed with SAC, and I don't even think we use store, but we use as. We'll find out. The video will tell me. So users was causing us a little bit of grief, right? Users, no users, it's a recursive join. And if I want to see the tail of a traversal and I want to see that I have to carry those attributes forward using as, it'll be easier if I'm not using a recursive join. Recursive join is what I want to do. Users, no users. Who do you know? What movies are they rating? But let's digress a bit and let's do users place orders or users ordered orders. The data sets are a little more distinct, and showing you as, pardon me, will be easier without a recursive join. Works perfectly well on a recursive join, but you might get a little confused as you're first starting. So we already have users, we have orders, the classic, users and orders. And the intersect, the edge between the two vertices of users and orders, could have called it placed order, you could have called it whatever, I called it ordered. Users, ordered orders. Placed order seems a little more attractive right now. And this would actually be an edge that has a property. So what are the two mandatory keys in this edge? It would be the primary key of one vertex and the primary key of the other vertex, which user placed which order. And then I have an additional property key to this edge called the order date. I threw that in there because I wanted you to see that. And the whole reason we're doing user orders is because the recursive join of user to user might have been, all of a sudden my nose itches, a little confusing to you as we show as. The data then, we already had some users, Farrell, Q, Denise, whatever. And now that we have two new tables, we have orders and ordered. We should probably put some data in there. And the CQL select insert statement looks just like SQL. And I deleted some words here just to fit it on the page. So I inserted into orders, 4 orders, order 101, 2, 3, 4. And the orders were just singular, beers and chips, wine and cheese. Farrell placed 2 orders. He placed order 101, he bought beer. Farrell placed order 102, he bought chips. Denise is a little more sophisticated than me. She bought wine and cheese. I don't actually drink beer, but you get the point. So here's 2 different queries then, and the whole point is we're getting ready to show you as. So let's use this also as a checkpoint. What do we remember? What do we know? So I'm looking at user Farrell. G.V, starting at basically all vertices in the graph. I want to start at just the vertex called user. And I'm going to filter out of user the user ID Farrell. So I'm just looking at Farrell out of users. And value map true. Value map true is a good debugging thing. It'll show you not only the ID and the label, the 2 meta columns, ID and label, but it'll show you every column in the vertex or the edge. Depends on what you're querying. So if I report every column from this vertex, I see the ID and I see the label. Those are 2 meta columns. And I see user ID and I see age, but I do not see gender. And the reason is Farrell was added without a gender. I didn't realize there was so many pages, or I might not have done this. Farrell was added without a gender. And so just know that we have jagged rows, and nulls are not returned to the calling function. It's an optimization in our storage engine. So here I see that Farrell was returned without a gender. Do I still have my pointer? I do not still have my pointer. But Denise was added with a gender, so that's why same query, 2 different rows, I get 2 different schemas in response. Oh, it's right here. I thought to put it on the slide. I forgot I put it on the slide. So the whole point of this is I ran a query against this vertex. I do a value map true. I get all property keys that are in scope. Feral didn't have a gender. And these are the result sets, jagged rows. So users table, query the users table, what property keys are in scope. Differentiate that with this traversal. So g.v, I'm looking at all vertexes, just the vertex called user, and I want to leave on just feral, just the user in the users table called feral. And I'm going to go out on an edge called ordered and show me everything that's in scope. Because of the true, I get the ID and I get the label. This debugging step of value map true, I wouldn't need this in production, shows me that I'm on the edge because it says here's your vertex or edge label, table name, and I call my edges E, and E ordered I know is an edge. And the only other property key that is in scope is the order date. I thought that was funny. That's the edge from YouTube. So out on E, the point is value map true. I no longer have in scope any property keys from user. They're not there. And then just to beat a dead horse, how about that for a, what is that called? An idiom? Euphemism? I don't know what it is. G.v, go out on user. User ID, feral. Ah, interesting. And I'm sitting on a vertex called user. You know that because it says has v user. And out is a vertex traversal step. It is only in scope when you're sitting on a vertex. And where does it go? It goes to the adjacent vertex. In this case, users ordered order. And so let's prove that. Here's the label. I went to orders. Users ordered orders. That's what is in scope, value map true. I have the ID as a meta column, I have a label as a meta column, and I have the item, and I have the order ID. That's what's in scope on orders. That's why we went to these new tables. If I did users, no users, I'd be back at users, it wouldn't be clear. The point is, I went from vertex through the edge to the next vertex. What determined that? The out step. What was in scope? Whatever vertex I landed on, I happened to land on orders. Good to go? That is a marketable skill for graph traversals. Traversal steps and how you get from vertex to edges. There were like 10 or 12 methods. You need to know. What did I choose? Did I choose out or out E? Where did I land? Where did I start and where did I end? And you can actually think of it in the whole graph of you have a current, where am I? Am I on an edge or a vertex? And that determines then what I can execute. I can't go from edge to edge. I can only go from edge to vertex. From a vertex, I can go to an edge or the adjacent vertex. That gets a little, it's not entirely as simple as that because your traversal can actually branch. But in that context, each of those traversers would be sitting on an edge or a vertex, right? So anyway, that's why we did this little progression to show you what is in scope. And we can control that with as. I can carry forward property keys using as because honestly, sometimes you need them. So let's read this one. G.v. I started the whole graph. I started every vertex in the graph, specifically the vertex called user, and I look for just feral. So starting in user, start with just feral. Later, I will have access to whatever property keys are in user. I'm going to say as user. I could have called it as T1. It's like in SQL, this would be like a table alias. I'm going to go out, which says vertex to vertex through the named edge. If you don't have that memorized, go back 8 slides. Out is a vertex traversal step. It must start on a vertex and it lands on a vertex. And how does it know what vertex to go to in a complicated graph? It goes out through the single or set of named edges. You could also leave this null and go out through any edge, but what are you trying to accomplish here? And when I land there, another vertex, what vertex is user connected to through ordered? He's connected to orders. I'm going to call it order, again, like another SQL table name alias. And where previously we had done a value map, This time I'm going to do a select and say, give me everything from user and everything from orders. This would be the equivalent of a two-table select in SQL. Select star from two tables in SQL where the tables are joined on an equality. It's a little different than a SQL select because we didn't talk about the storage model yet, but the edge between two vertices is minimally the join pairs, the primary keys that the two tables are related. So in a graph, all tables are pre-joined. It is ridiculously fast. They specify a relationship between two entities, two vertices. And that's all the data there. So that's everything that Farrell had ordered. And hopefully it says beer and chips, and it says beer and chips. If you're wondering, if you're really into JSON, love JSON, by the way. If you're really into JSON, why is order not an embedded array to user? Why is user redundant across these two rows, right? Why is an order an array to user? That might have been, it's another valid way to represent that in JSON. And that's because this out with the as, the way it's constructed, it's largely the equivalent of an inner join in SQL, and that's why the data is returned that way. Love it or hate it. If you wished that order had been an embedded array to user, you can certainly munge the data in the traversal, but that's not how it comes by default when you're using as. So applying the as back to our actual use case of do users know each other. We saw earlier that Farrell could know people. People could know Farrell. There were people who knew Farrell who Farrell didn't know. But if I want to report only the situation where people definitely know each other, I have to look at both sides of that relationship. And so let's do that now. And to do that, we're going to use the as. The as can be used as what we'll label as a carry forward, carrying property keys from customer, places, order, downstream, and then you can just print those values or return those values. But it can also be used in calculations and in intersections of tables and others. So let's pick this apart, and we're going to give special attention to the line that's identified as this line. So G.V, starting at the top of the graph, every vertex is in scope. I'm just going to look at the vertex user, and in the vertex user starting with Farrell. We're going to say, who does Farrell know? We're going to call that A. So that was the 4 rows, right? Farrell knew 4 people. We're going to go out from knows again and pull another data set and call it B. So who does Farrell know is A, and then out again is B. And we're going to say where basically the key from B equals the key of A. And we're going to return these 2 rows, select A and B. What this query does for us is return not only who does Farrell know, A, but who knows Farrell, B. And those 2 lists must fully intersect. This second half, this B and who knows, would have returned that Dave shady character who Farrell doesn't actually know. And because Farrell doesn't know Dave, even though Dave knows Farrell, Dave will get disqualified on this line. So this construct of as out, and then do an equality will tell you it's a bidirectional relationship. Farrell knows them, they know Farrell, they know each other, not just I know Bono, right? Bono has no idea who I am. An example we've beat to death. And then this last little block is really just the what do I want to output. That's a pattern we use frequently, and now you know how to do it. So going from our example of Farrell, Denise, blah, 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 which really just has users and knows and beer and wine and blah, blah. Let's go back to Killer Video, which has hundreds of movies and hundreds of people. And for whatever reason, they've obfuscated their names to call them U1, U2, etc., as opposed to Dave, Matt, and Sally, or whatever they are. Let's take a look at this query. G.V, sit in the graph. All vertices are in scope. There is a G.E, by the way. You can start at an edge. It's not terribly common. Just the vertex known as user and just the user ID of U1. Finally, not feral. And what is in scope? We get the two meta columns of ID and label. We get the gender. We get the user ID U1, and apparently they are age 17. So this is the row U1 in the user table. They're a 17-year-old male, and they're known by the name U1. This is just the table. So there is a user. And if we say, okay, who does U1 know and who knows them? This is the construct we just had. We go out and we say, who do they know? And who knows them? And where are they equal? We get no data. So that's unfortunate. Could be this person never leaves their basement, but they watch a lot of movies, but they know some people, but they don't know them. Let's do a little debugging on this, right? So let's just first of all confirm who they know, user U1. User U1 apparently knows 4 people, all children, that's good, he's a child. Not going there. G.V, user U1, who do they know? And they know 4 people. The out will go to the adjacent vertice and the incident records within that vertice. So this is the 4 people that U1 knows. So he knows 4 people. We're good so far? We're debugging why they don't know each other. Like people he knows don't know him. So he knows 4 people. If we see who knows him, user U1, we see it's only one person, and it's user 199. And I probably have it on the next page, but I'll go back one. User 199, and there is no user 199 here. So this explains why the construct of who does he know and who knows him returns no rows. He knows 4 people. None of those 4 people know him. One person knows him, and it's none of the people he knows. It's probably some sort of gaming website, right, is where we got this data. I actually don't know. And if we run the both construct, the both vertex traversal step, we see that we get all 5 rows because they were distinct. He knew 4 people, and one person knew him, and those 2 data sets did not overlap. So moving forward, at least user 1, U1, there was no shared who does he know and who definitely knows him, not like with the feral example, but at least they know of each other or they have a sense of each other. So we're going to progress with probably both, or later we'll look at least who does he know and what have you. Let's do a checkpoint. We've been talking for a while. You gotta be kidding me. Umpteen pages just to do a join? Well, no, it wasn't just a join. This was an intersection, or you could think of it as a difference of 2 data sets to confirm a bidirectional relationship. Who does feral know and who knows feral? And another reason it was umpteen pages is we're beating to death, out and out E. We're trying to set a baseline so you have a construct. We talked about the fact that for efficiency, as you run your traversal and you hit each of these steps and each of these vertices and edges, you're not carrying all of that data you could potentially touch. So you use the as step. You can use it to put property keys in scope later for reporting or for evaluation along the way. So we did quite a bit. We didn't just do a join. If we did a join, it would have been 1 page. We actually did do a join from customer to orders, and that largely could have fit on 1 page. We're building, we're learning. So we did has, and we did has label. When we leave a vertex and we do a has, we can specify the vertex name or the edge name and a singular set of property keys and expressions to them. The default is an equality. If you just want to leave the vertex with no predicates or the edge, you can say has label. We did the vertex traversal steps and some edge traversal steps. So that was all of these. That's why we were doing several pages, in, out, both. You actually did everything on this page. We did as, and then carrying the keys minimally as we step from vertex to vertex. We could do a where 2 people actually know each other, or etc. And we used value map true, and we did select by. So we actually did quite a bit. And what we have so far is It's okay to know somebody, but did they know you? Do the two of you actually know each other as opposed to like know of somebody? And we're going to move from that to a wider circle of influence. Okay, so you know them, but maybe how well do you know them? Do you have 2 friends in common? Do you have 10 friends in common? We're going to do that, and then we're going to go further still. So we're looking at, classically, graph, a network of data to be able to form the best recommendation possible. So continuing then, we had previously covered in the graph people you know. But we want to go farther. We want to go into the people you know, and then not only who do you know and they know you, but who do you both know? Who do you have in common? What is your true circle of friends? And the reason we're doing that is we're trying to assemble data of a collection of users and their likes. I'll share with you first, we're going to do who do you know, which we've done. And then who of the people you know do you know in common? So who are their friends? Who are your friends? Are they the same people? And then we're going to go farther. What movies did they like? Did they like the same movies? And use that to form a recommendation. So let's go a step further. Let's look at this query. If you get this query, you are well on your way. If you don't get this query, you should watch this portion of the video twice, draw a picture, whatever. This is a money shot query. Let's do it. So we're doing users know users. We've done some of this. We're going to go farther. G.V has user ID, Farrell. So we're starting in user with just Farrell. When we go out on user, E knows. Here was the whole data set, but when we say who does just Farrell know, we get these 4 rows. Farrell knows Q, Farrell knows Denise, Farrell knows Morty, Farrell knows Hatcher. We landed on knows. And what comes into knows on those 4 rows? We were on user, just Farrell. We went out on E knows. We got the 4 people Farrell knows. We landed on user again on just those 4 users. When we do an in following the out, we get an additional set of rows. We get the people that those people know. We get the people Q knows. Q knows Denise. We get the people, and Q knows, Farrell knows Q. Q knows Denise. Farrell knows Denise. Who does Denise know, right? And who does Hatcher know? But the point is, the way this is written, first we go out by who Farrell knows, and then we go in on that list. We wind up getting just the users known by 2 people. So Farrell has to know them. Farrell knows Q. Q has to know them. Otherwise, they don't make the list. Farrell knows Denise. Denise knows them. Otherwise, they don't make the list. Farrell knows Morty, but Morty doesn't know anybody, so he gets kicked out. And then Farrell knows Hatcher. Hatcher knows people. But what gets returned as a result of this in-out is people known in common. Not only I know Q, but Q knew people. And then did I know those same people as Q? Out and then in. And as it turns out, if you don't have this filter removing Farrell, Farrell will wind up knowing Farrell, and big deal. We could have guessed that, right? You'd hope so. So the structure of out and then in from that result set, the out was who does Farrell know? And then the in attaches who do those people know, who Farrell knows. It's a circle of friends. And we, as said, we filter out Farrell, and then we do a dedupe because Q knew Denise and Hatcher knew Denise, but okay, that's repetitive, right? So after the dedupe, I get Hatcher and Q, building a circle of friends. So who did I know? That's one thing, but they had to know people whom I also know. Only Q, if you go through this list, knew people I know. Only Hatcher, pardon me, knew people I knew. I knew Denise. Denise knew me, but we didn't know people in common. Good to go. That's a pattern. That's something we use often. And if you need to pause and spend a moment on this, this is not only a query we're using forward, but it's a key comprehension of graph. It's a circle of friends. Not only who did I know, but who did they know, and did I know the same people? Again, I know Hatcher, Q, and Denise. I knew Morty, but Morty doesn't know anybody. I knew Denise, but the people Denise knows, they're too cool for me. I don't hang out with those people. I don't know them, so Denise gets disqualified. Denise and I do not have friends in common. But Q and Hatcher, I know them. They know people. I know those same people, thus they get returned. And let's go further. So, okay, big deal. I knew at least one person that Hatcher and Q knew. But, okay, that's interesting and it's important. It's better than Denise, right? I knew Denise, but I didn't know any of Denise's friends. But what if I want to see the strength of that connection? I want to know not only that Hatcher and I know the same people, and Q and I know the same people, but we know a lot of people. And for that reason, we're going to add a new command, and it's with SAC. With SAC was introduced earlier topically. It was compared to as. As you go vertex to vertex, through edges or whatever, you have to go through an edge, but whether or not you actually stopped on the edge, you went out.e. As you go vertex to vertex and through vertexes and edges, you have no tail. You are not keeping the property keys that you might have witnessed on your traversal. If you wish to keep the property keys as you go through traversal, you can use as, and we called it a carry forward. The difference between as and with SAC. As is global to the entire traversal. With SAC, the property keys that you step upon, that you bring into scope, will be local to a traversal, to a traverser. They will be, think of a sack, like carrying a sack of groceries. They will be the people that only Q knows. As I went from myself to Q, that's only the people he knows. And as I went from Farrell to Denise, to the people she knows, that sack, there'll be a sack private to just Denise. And as I go from Farrell to Hatcher, the sack will be local to the traverser of just Hatcher. So they're like subgroups, whereas as was global to the entire traversal, with SAC is local to a traverser. And in this context, it means just Q's friends, just Denise's friends, whatever. And why do I need that? I need that because I'm going to start doing math on just the people Q knows, just the math of who Denise knows, just the math of who Hatcher knows. So let's pick this apart. I have my mouse and I have my pointer and scope. So start on just user with the user Farrell. We've seen that umpteen dozen times. Start with just Farrell. We go out on E knows. Here's E knows. Farrell knows 4 people. So this is a result of the as. The in we have done before. So this is going to add the people that these 4 people know. I know these 4 people. Who do these 4 people know? Morty doesn't know anybody. Sorry, Morty. Q knows Hatcher. Q knows Denise. Denise knows... Why did I leave Denise out of this list? Denise, does she know people? Denise knows Farrell, and that's it. Denise knows Dave, but Dave doesn't, Farrell doesn't know Dave. So this construct of in are just the people known by Denise, Q, and Hatcher, who Farrell also knows. I don't know Dave. He doesn't make this in. So as a result, I have this list after the in, but now I'm going to count. I'm going to say just for Q and just for Hatcher, and Denise didn't make our list because she didn't. Q knows Denise and Hatcher. Hatcher only knows Denise. And if I say group and count, sum of 1 is a count. If I say group and count, a sum of 1 is that. For each of Q's people and just each of Hatcher's people, Q will come back with a 2 and Hatcher will come back with a 1. And the GTE is short for greater than or equal to. So it's going to filter out Q and not Hatcher. Hatcher didn't know enough people. I know Hatcher. Hatcher knows people. We know people in common, but we didn't know enough people in common. And pull out any duplicates and return it, and here we get just Q. So one more time from the top. Who does Farrell know? Those people know people. Do we know them in common? That's all done by the out and the in. Okay, so we know people in common. But how many people do we know in common? I want to know that we know a lot of people. And so the construct of with SAC, sum, and one, it's a counter. And with SAC is global to each traverser. That means it's going to count for just Q. It's going to count for just Hatcher. There were 2 Qs and 1 Hatcher, so the numbers were 2 and 1. The comparison of the SAC, SAC is like the result, what's in the SAC. There happened to be just the one sum. Q was 2, Hatcher was 1. If it's greater than equal to 2, for Q it gets returned. Hatcher, it was 1, which is not greater than or equal to 2, so he got restricted. Pull out Farrell, I don't care that Farrell knows himself. Remove dupes, and there's the value map. I know Q. Q knows 2 people, I know the same 2 people. Good to go. You're seeing this for the first time. This could be really hard. So pause, go backwards, run it on the data. Every one of these queries, we do it baby step by baby step, but that doesn't mean you have it memorized, right? Go backwards if you have to. Rewind the video. If we move this is the same query as before. If we move this back to killer video, we did a little bit different. Instead of an out and an in, we did an out and a both, because otherwise poor user 1 knows 4 people, but only 1 person knows him, and they're not the same. So in effect, we get who does U1 know, and we also pull in the who knows U1, and they don't have to be the same. But we do the count. And we say whoever's in that list, it's a heavy list. And you could stop the query right here and do a value map and see who's in that list. We've done it before. Count and say, yeah, but they got to know at least 2 people in common. So while U1 only knows 4 and a couple people know U1, their circle of friends, they run in the same circle. And in at least one instance, somebody in that list, and it turned out it was U49, knew 2 of the same people as U1. If we change this or debug it, and we say, okay, and we've seen some of this before, who did user U1 know? He knew these 4 people. We did this before, so we're debugging. If we do both, here we move to U49. We're looking at it from the other end of the scope. U49 knew a bunch of people and was known by a bunch of people. That's why the both returns this. And U74 and U83 are in this list. U74 is known by U1. U83 is known by U1. If both U49 know these 2 users equal to U1, but only one of these rows is returned, they're not both returned, it's because they don't know the same high number of people in common. As witnessed by, what was it, query 8.1. That's why only U49 comes back. Good to go. Checkpoint. We have learned or seen previously. We had learned or seen previously. Has label. Out, both in and out E. We did as, we did where, we did value map, and we did select by. We just added filter and was pretty silly. We did dedupe, and we added with SAC. The hardest one on here right now is as and with SAC. As is a carry forward. It is global property keys to the entire traversal. With SAC is like a subgroup. So keying on just Q, keying on just Jim, Hatcher, just on Denise, with SAC and SAC. With SAC is like the declaration before any traversing is executed. It says I'm going to do a count, I'm going to do a sum 1. And then the reference to SAC says, okay, now I can evaluate whatever's in the SAC. And it was a numeric only because I'm just counting, I'm just incrementing. And I said if it's greater or equal to 2, return it. So what we have right now is, do you know them? And do you also have a high number of friends in common? Yay. We did that with SAC. Do you like the same things? Because if they don't like what you like, I shouldn't be grabbing a recommendation from them. Remember, I think we stay with killer video, because now we're going to start pulling in movies and likes, and I just didn't bother to build that out for the simpler list of Jim, Denise, myself. So you know somebody, you have a high number of friends in common. Do you like the same thing? So we're going to do user, no users. We've been doing that for a while. And now we're going to leave the rated movie. And if you recall, rated has a rating. How well did you like the movie? And this is what we're going to evaluate. So starting over then, we've never looked at rated or movies before. We're going to start with user U1. We're going to go out of the users, and we're going to do rated, and we're going to do a count. We're doing out E. We count the number of ratings he made. He's done 32 ratings. Okay, great. User U1 has done 32 ratings. How many ratings did they make that were 8 or higher? So we start with the user, all of their ratings, and then we do a has. The rating had to be 8, 9, or 10, and do a count. So of 32 ratings, previous page, only 15 are high. Here's the magic. Now that I know that you've rated 32, you've rated 15 high, let's go back to people you know, and are you rating the same things? If they're just totally in the classical music and you're into rock and roll, I'm not going to do a recommendation, right? So let's pick this apart. We're going to look at user 1. We're going to look at movies rated 8 or higher. Starting from the user table, user U1, what has he rated? What has he rated 8 or higher? Where am I as a result of this out E? I started on the vertex user. I left with an out E on rated. Where does out E land? Out E lands on the edge. It's the edge of all the ratings for movies. I landed on the edge of ratings, and I said, just give me a subset of what I've rated. Just give me the 15 that I've rated 8 or higher. Good to go? That's where I am on the red line. Just give me the 15 movies I've rated 8 or higher. From that edge, I'm sitting on an edge. I'm sitting on out E. If you don't believe me, do a value map true. You'll see the label. You'll see the keys. Come in to that rated edge. I'm only going to, there was a mosquito. When I come into that edge, I'm only going to look at the ratings that are 8 or higher that I've made. I'm not going to look at every rating, just my ratings 8 or higher. And I'm going to come in from the adjacent vertex. And the adjacent vertex I'm going to come in from is users. And I'm going to come in from the ratings that they have made 8 or higher. So I have myself on the vertex user, and I have the ratings. And I'm going to come in from users again. I apologize, it's a recursive join. I have 15 that I did 8 or higher. The users that come in only will match with my same rated 8 or higher. As per this construct, I did an out E. I'm sitting on the edge. I come in V in E. Other users who have rated, and what this has, 8 or higher. Good to go? 962 times people have rated the same ratings. The same ratings is on a movie. The same movies, 962 times, other people have rated the same movies 8 or higher. You good? This is a pretty powerful construct. Look how small this is, too. I'm not saying this isn't hard if you haven't seen Graph. Back up, watch it again. What did I rate 8 or higher? Only that data set. What has a relation to that? What users have also rated those same, and what are we rating movies? Those same entities, those same movies 8 or higher. And that's happened 962 times. And look how small that code is. You could do that with SQL. It'd be a heck of a lot more code. We will show you the data on the next page. We're going to do this a little harder. Again, the magic is still in yellow. Let's walk through this. Starting on users, just user 1. What has he rated? What has he rated 8 or higher? Let's call that A. Those are just the 15 movies I've rated 8 or higher. I'm coming in from users to that list in V that they have rated 8 or higher. That's 962 times. I'm going to call that B. That would get a little ridiculous, so I'm only going to print 5, and I'm going to print A and B, me and them. Good to go? I'm going to do that 5 times. You know this construct. We did as. We had several pages on it. Limit, I don't need to see 962, I just need to see 5. Print all 962 if you want to. Pull it in a spreadsheet, I just need to see 5. Here's the data. So in this data, where's my mouse pointer? User 1 has rated a movie of 10. It was movie 567. Sadly, I join with myself. Here I see user 1 and user 118 have rated a movie 567. I gave it a 10. He gave it a 9, or she. User 1 and user 119 rated movie 567. It's always going to be the same. Because I limited 5, you only see movie 567. But in each pair, it's always going to be the same movie. I rated it a 10. User 119 rated it an 8. I rated movie 567 a 10. We're only on 567. That's why they're all 10, 10, 10, 10. User 125 rated it a 9. And then lastly, user 143 rated it an 8. I only showed 5 rows of data because, honestly, where were we going to go through 190 some odd of these? But what you have is me going into rating 8 or higher, somebody else coming in rating 8 or higher. The rating was on a movie. Why is movie on this edge of rating? Because you rate movies. We could go back to the data model. Users rate movies. And I'm coming into rating as a user, and I went out of user into rating, and I came in from user into rating, and that's why I get those column joins, if you want, relationships of we rated the same movie. Good to go? The only movies that would be in this list are movies that I rated 8 or higher, the 16 or higher. And, you know, if 1 million people rated these same 16 movies 8 or higher, well, there you go, right? And that was all as a result of this little query. That's pretty tight. We added something to this. Remember on the last page, I showed myself rating the same movie. Well, that's pretty weak. I want to get rid of that. So here's how we tackled that. I don't need to know that I like the same movies that I like. That's pretty silly. So I can take that out with this. And if I'm looking at just users, I'll put a dedupe on that, and then I'll do a count. So not myself and removing duplicates, there's only 599. And what was the original number? Like 962 or something like that. Some people had rated, well, anyway. Unique user list. I don't need to know. If one user rated 3 movies that I liked, they would have shown up 3 times. So I rated 3 movies. They rated the same 3 movies. They'd show up 3 times in the list. I just want their name. And so that's what the dedupe gives me is, and then it's 599. Here's the data. The difference between this page and the last page is instead of doing a count, I do a value map. Again, I do a limit 5. And how did I do the A's and the B's? I didn't do A's and B's. So here are just users who rated movies that I rated. These are the users. Don't know that I need the pen here. So here are the users. It gives me demographics about the user. If I wanted to use that at any point in my query, I don't. But checkpoint. Where are we? All right. So you found somebody you know. You have a higher amount of friends in common. And you like the same things. Okay, that's interesting. But do you like the same things a lot? We're looking for the strength of the recommendation. Not only do you know them, okay, great. And we know how to know, do they know you too at the same time? That wasn't represented in the killer video movie dataset for user U1. But do you have a good number of friends in common? Maybe 2 is not a high enough number for you. When we go 10, we'd have to look for somebody. But do you also like the same things? Because if you don't like the same things, what kind of recommendation can I provide? And then lastly, do you like the same things a lot? How often does that happen? If only once we like the same thing, I'm not going to accept your recommendation. We have to like the same thing a lot. And you know that when we're counting per user, when we were counting how many people does Q know who I also know, how many people does Denise know who I also know, you know that when I need a variable per traverser, per subgroup of the traversal, you know that I use SAC. We did that before. So we're building towards like the same things a lot. We're going to do user 1, the rating must be 8, and you have to like the same thing 5 or more times. So per traverser, we're going to do a count. That's what a sum of a 1 is. First time you have it, you sum 1, it's 1. The second time you sum 1 to 1, you get 2. Third time you see it, it's sum 1 to 2, it's a counter. So start with V, user ID U1. What has he rated? Pardon me, what is he rated 8 or higher? And you know what this construct is. Of that subset list of 16 movies, who else has rated the same 16 movies 8 or higher? And then we go out. We had this on a previous page. What we're going to get here is the user. And we say, how many times have they rated? And it's not me. It's not equal to myself. Did they rate 5 or more times? Dedupe value map. Here's the data. These are users who have rated the same things that I have rated 5 or more times. We like the same things a lot. They rated it 8 or higher. Checkpoint. Movies, friends, likes, and the amount of times we like the same things, the affinity of likes. That seems pretty trivial, right? And we took 1,100 pages to get there when we were teaching you graph. But that seems trivial. Movies, friends, likes, that's trivial, right? Absolutely not. Push the chair away from the desk for a moment. Now, if that seemed complex, and I will grant you, it could have seemed complex if you have not seen graph ever. We tried to explain it slowly over 20 plus pages, but still it's complex. This pattern is prevalent. This is the very same pattern we use for entity resolution. So while we were looking at who do you know and do you like the same things, work with me here. That same pattern could have been, did 2 people go to the same place? Do they have the same address? We use this same pattern for, are these two people, Dan and Danny, are they the same person? We use this in fraud. We use it a lot of ways. People will try to obfuscate their user ID by using their middle initial or not, or their full middle name or not. But if they're doing the same things, they have the same activities, they go to the same locations, they have the same, and then we can put a score also on any subset of their identifiers, name or other. We can start to guess that they're the same person. In this use case, we're just like, are they your friends and do they like the same movies? But if they're both called Dan or Danny Farrell and they're pinging the same cell towers and making the same, we could use it for entity resolution. We also use it across vertices, time, location with someone implied, for impact analysis. This is almost a reference to the story I did earlier, Denver, Minneapolis. I'm making a shipment. How does Houston fit into that match? You could do that manually using these same techniques. As it turns out, for that use case, there is a distinct operator to do all that work for you. It's called match. But if that seemed complex, practice makes perfect. You're seeing it for the first time. You're not used to having a query environment where you can program the traversers. You're not used to having 40 steps as opposed to 5 optional clauses. But in an amount of time on graph, you'll be able to read that with your eyes closed. I'm going to say 3 days, 5 days, 1 day if you're sharp. And that's a pattern you use all the time. the bottom of this page, that was manually programmed imperative because there's just no operator that says, first of all, it would have to know your vertices and your relationships, but who do you know and have a large number of friends in common? Additionally, those commons like a high number of the same things. Then I'm going to put them in my short list for recommendations. How many operators would your language have if it, had a pre-built for that? And you can library these and make reusable code. But that's a pattern we use all the time. And it would be it would behoove you to, if you didn't get it the first time, print it, put it on your cube wall or wherever you work, or go through it 3, 4, 5 times. Actually copy and paste the code, run the code, because it's a pattern, one of several, but it's a pattern you will use all the time. Those are base skills you will use all the time. Previously, we've seen has label, the traversal steps for both edges and vertices. We did as, where, value map versus select and by. We did filter, and in greater than we did dedupe, limit, count, and with sac. Probably my favorite on here is with sac. As is global to a traversal. With sac is like a group by. I hate calling it that because there is a group step that does a similar function. But with sac is the bomb. And you can also, when you specify the with sac, you don't have to just count. You can do booyah stuff in that parentheses and multiple stuff in that parentheses. We add side effect and where without, and you will be able to do a product recommendation engine using Graph. Overview, what are side effect and without? We start with the movies you like, but then we cull that list by how many times do you like that? And, what's the affinity? But ultimately what we want then is we want to go back to our movies and say, give me a recommendation. And so side effect and where without are going to allow us to do that without re-querying the data. You could think of it as it's another variable collection or data set collection, but not equal to sac and with sac, or certainly not without as. Unlike SQL Select, if you were to argue to me that SQL Select can do everything that we've just done, I'm going to nod and say yes. Ours is this long. And you didn't know it when you walked in, but it's this long. We're going to add like 2 or 3 more lines, but it's this long. The SQL Select is going to be at least a page and a half long, and you're probably going to use temp tables because SQL is always just a top-down single pass, and you got to use CTEs to do the intersects and blah, blah, blah. Everything we've done is streaming in memory, ridiculously efficient. And in Graph, all of the tables are pre-joined via the edges. It's stupidly fast. And that's why we're going to use side effect and where without, because we need that data downstream. So we don't recommend to ourselves movies we've already seen. The programmability of Graph traversals is killer. So we're gonna show you how to use where without and set up for it. So let's build slowly as we always do. We've seen this before. We've seen it multiple times. So we're going to leave user just the named user. What have they rated? They've rated 32 times. And then we said, okay, but what are the things they rated highly? Previously, we did a greater than or equal to 8, and we got the high movies. To give ourselves a different data set on ratings and to show you the where without, this time we're going to grab the movies we rated poorly, which is less than 8, LT, less than. And hopefully the math adds up. 32, 15, 17. 17 plus 15 equals 32. So these are the movies we don't like. And we're only doing it so we can get an isolated data set to show the where without. So here were the movies we rated highly. Good to go. We rated 32 total, 17 poor, 15 high. Nothing here should be terribly new. This slide in and of itself does nothing. We're introducing side effect. But we don't actually use it yet, and we don't actually use it. You see that you still haven't filtered. We're still outputting all movies. And then this next slide is the money shot. So there was an easier way to do this. We've already done the easier way, but that wouldn't have demonstrated how to do side effect. Let's pick this apart. G.V, just give me user U1. Side effects. So this is going to give me a data set I can refer to later. It's going to be like a temporary result set in memory. And I'm going to label this result set as A. What is this subset? Remember, we've rated total 32 movies. We're going to go out on rated, and we're going to say the rating is less than 8, so that's 17. So this data set is 17. Side effect, think of what the word side effect means. It kind of puts it on the shelf and says, okay, imagine that didn't happen. The traversal is going to pick up from here. So the side effect executed, but it puts it on the shelf. And it picks up the traversal as though the side effect had never happened. You good? If you get that sentence, you get it. So just leaving g.v, I ran a side effect and I put it on the shelf and call it A. And it was everything I rated poorly, which was 17 rows. After the side effect, the traversal continues as though the side effect had never happened. So when I do an out E on rated, I'll get 32. I can now do a where without refer to the A, which was 17. 32 minus 17 is 15. Yay. So that was stupid because I could have just said, well, why don't you just give me greater than equal to a rating of 8 and I would have gotten the 15. Was not the point. The point was I can put a result set in my traversal off to the side for a later reference. Why do I need that? Because I'm going to get a set of recommendations from these people I know really well. And in that set of recommendations is going to be movies I've already seen. And I don't want to recommend that. That would be stupid. So once I get the list of what I've already seen, I'm going to side effect those. And then I'm going to go about my processing as normal, get recommendations. And I'm going to remove, as you might guess, movies I've already seen. So that's why we have side effect. This is the same view as the last page, but we'll give you the data, and you'll see that the movies are high. Again, you could have done this more efficiently, but we needed a way to show how to program side effect. You now have all of the techniques to do a product recommendation engine using Graph. It's not a product, it's a user, it's a collaborative. You've seen it before. You have all the techniques. We picked them all apart, took a dozen pages. Here it is. You've seen this before. I'm still not saying, okay, turn off the laptops and write this from scratch. First of all, why would you when you have this resource? But this is what we saw before. Let's pick this apart and see if we get it. And I'm hoping you can at least say, okay, I don't have this memorized, but I see where he's going with this. With SAC is going to allow me to count later. I don't know yet how I'm going to count. V, I'm starting from a vertex. I'm starting from the vertex where the user ID is just me. Side effect. The side effect starts here. I'm getting the users, and I'm going to call it movies seen by user. Remember that user U1, he knows 4 dudes and only 1 dude knows him. I filter out the high-rated movies. This gives me the high-rated movies that my friends have seen. I take out the high-rated movies that they've seen. I take them out from my movies. I don't want to recommend my own movies. And then order with a limit, value map, movie, title, and year. The side effect will be the movies that I've seen, my movies. I didn't pick that apart very well. Let me do it again. The side effect is all on one line. Up here, I have just me. The side effect is every movie I've rated. Outrated, aggregate, I call it A. Call it SE seen by movie. So this, put it on the shelf, is every movie I've seen. I call it bad and good. I might have rated it poorly, but other people are going to rate it high. I still don't want you to recommend it to me. I've already seen it. I call it SE seen by movies, or seen by user, and here I suck those out of whatever gets recommended to me. Between these two lines are people I know well, although I did a both, because remember he only knows 4 and 1 knows him. And what did they rate highly? And what did they rate highly? But from people I know really well. Order and limit. Let's look at the data. So based on this data set, Is that the Simpsons movie? I'd have to look that up. One Flew Over the Cuckoo's Nest, The Pianist, The Good, I don't even know. Oh, The Good, Bad, and the Ugly. Of course I know what that is. And then Forrest Gump, fabulous film, 10 or 11 Academy Awards. And that is this query. So I don't expect you have it memorized. I wouldn't expect you to have it memorized. I would expect if you watch this video once or 3 times, you would have a sense comprehensively what it does. And I would have a sense that if you go through each of these iterations, how many pages did we take? That you could go slowly, right? Okay, these are people he knows. These are the people that he knows who they know, and then they're in common. And not only that, but do they know a lot of people in common? And what movies did they rate highly? And, is that a recommendation? But don't recommend movies he's already seen. You got to walk through it. This is officially 1 line of code, even though it's a Fluent API, and I'll still say it's 1, 2, 3, 4. It's like 10 or 15 lines of code to go through a graph and do a movie recommendation. And there's the data. So, customer, I'm confused. That was the original problem statement. I saw a presentation. Hey, product recommendation using graph, a product recommendation using analytics. The analytics one, out of the box, can build a map that you can score from in 2 lines of code. But it's a content based. You have to have the data. It's grocery store receipts. People bought flashlights and batteries. There's an affinity between flashlights and batteries. You have just flashlights, I'm going to recommend batteries. And I will have a sense of how strong this recommendation should be and how successful it should be. Of course, I'm going to capture that. If I give you a coupon or people who bought X bought Y and you don't actually follow through on that, I need to know that. But it was content based. It was item or product. If you don't have that data, you don't have item data because the movie hasn't even been released yet. Only reviewers have seen it. You can't do content. Data doesn't exist. So you do collaborative. Your friends like this, they like it a lot. You have 100 friends, but these 10 really seem to like what you like. You might have friends who don't like what you like. You like other things. But in this area, they really like, you have a lot of shared interests. And they've recommended something you haven't seen. I can do that collaborative base using graph, 1 line of code, but okay, maybe it's 10 or 15 based on how you count. That was functionally how to program that. Because graph sits on top of Cassandra using primary keys. Primary keys are uber fast. The data is pre-joined. This is a very performant engine. Graph, and specifically graph, scalable graph, should probably be in your toolbox for predictive analytics. Item, product. Spark, collaborative, content-based, or collaborative-based, use graph. You have both. You have all the code. We listed the URL on the first page. I need to give a shout out. Dave Beckberger is one of my teammates. Fabulous dude, ridiculously smart. He's also writing a book. Look for it. I'm writing a book on Gremlin. Great guy, great resource. Always answers my questions. And Dr. Artem Chabatko was actually from the problem statement. He only had 50 minutes. He gave at our user group in 2019, he gave just the graph piece, product recommendation engine, and that's where the customer said, well, I've seen other product recommendation engines. Can you do a compare and contrast? That was outside of scope for what Artem was doing. And I took Artem, he only had 50 minutes, took his, he did a progression also, but I really split apart side effect and as, because I didn't expect you had seen him. He had to expect you had seen him because you were sitting in a graph presentation. So thanks to David and thanks to Artem. Don't forget where all of these slides and blah, blah are, data, the query, all of it is there. Hope you enjoyed this video. I'm sorry it was long, but it was a primer on Gremlin, and this was an above average difficult query. But hope you enjoyed it. I hope you find it useful, and I will see you out and about.